In this video, we're going to talk about data types in Java and also look at various properties of data types. We're also going to further explore loops and the switch statement. Before I get started, I would like to close my previous project, and I also strongly recommend that you do the same before you begin your new project. Just say close, right click and close in NetBeans. And so now I'm ready to say file, new project, Java with end, Java application, all the settings like this. I'm going to name it week 6. And I will create the main class, which will be main app. I will create the file which will contain the main class. I have the tendency to make the name of this class recognizable. And this is my previous location. Of course, I have kept all of my projects in the same directory right here. My directory structure is pretty simple, so this is where I'm going to keep going and continue adding my projects. Okay, so this is week 6 project, finish. And of course the file is created, so I'll just update, just remove the comments for now to keep as much space as possible to be available. I have a habit of marking endings of corresponding braces with the names of methods and classes that I am going to have in the source file. So now I'm ready to save it, so I have my new project ready to go. The first thing that I'm going to open is the reading materials, which will of course give me access to the presentation. And also I will open the code examples here before I go to our current weekly assignment. So first, the reading materials. Today's handout is right here, control statements, but it also includes the conversation about the data types and their properties. So I'm going to open this presentation today. This is the presentation that we're going to follow. Also, we're going to look at a few examples, our coding examples right here. So we'll come back to this page a little bit later on. And now on to our weekly assignments. So here we have our current reading assignments, and of course we also have new homework, which is computing prime numbers. We're going to discuss that a little bit later on. So first let's start with the presentation. Okay, so there are 8 primitive data types. This is kind of interesting term, primitive data types. It also stands for fundamental data types, also known as basic data types. These data types are understood by our hardware directly. That's why they're called primitive data types. This also means that individual CPU instructions, basically our hardware, can understand these data types in memory directly and is capable of doing computations with all of them. So it can multiply bytes and add bytes, and likewise it can multiply integers and so forth, and can multiply and divide doubles, right? So there is no additional steps to parse these data types. They're not complicated data structures. They're just ready to go in computer memory, and the CPU can do operations on them directly. That's the reason they're called primitive data types. Right here you can see the ranges of the values. So the byte is basically a very small integer. It just ranges, like it has 8 bits, which is 1 byte in size, and its values range from -128 to 127. The next one in line is a short integer, which is also an integer, which is just in a little bit bigger range. Basically, it's like 64 kilobyte range right here. Then we have an integer, and that's just a little bit bigger. So this is bigger range, essentially it's, if you think about the space here, if this was used as a, say for instance, memory address, this would give you a coverage of 4 gigabytes in memory. Long is a long integer and it's quite large, so this is like astronomically big number, which can be already used with all sorts of scientific computations, like taking exponents of large magnitude, like big powers and so forth. And we have two kinds of real numbers. These are all integral types. They basically have no fractional part. The two floating point data types is a float, which is sort of like the original type of float in computing in general. And notice it's typically on most hardware platforms is the same size as integer. So basically, if my integer is 4 bytes, it's very likely to expect the floating point number also be a 4 bytes in size. However, in most cases, you would prefer to use double because this is de facto standard. This gives you the highest level of precision, and it's just de facto standard data type to do all scientific, financial, business computations, and today we'll see some examples of that. Character, of course, is to store characters, and these are the characters that are captured by our string class. And I say here it's a Unicode character. What it really means in computer memory, that characters in Java are 2 bytes. Some C and C++ programmers are used to having character of being the same size as byte, but in Java, this is the reason why we have the byte data type. If you need the byte size data type, character is sort of like special role, is a Unicode character, and this Unicode really means that this is a number that is the same size as short, so it has the same range, but it's only positive values. It does not have negative values. Characters, if you think about them as integers, they're always positive values. So if you expect to use, or if you're planning to use character as a counter somewhere, it will be in roughly in range of 64,500 something, and it will be positive only values. That's just your information about the character data type. You really don't have to worry about any of this. However, once in a while you can make a decision like which of these data types to use. Most of the time you'd be using integers and doubles for most computations. Everything else is just more special case for situations where you need either less space or bigger range of numbers if you want to choose something different. And of course, characters are inherently used by the string class. So these characters are encapsulated by the string, Java string, and that's what it's using to store characters. Now, Unicode is type of encoding, which is now universally accepted as an encoding of international characters on the internet, on the web. Okay, so there's also this Boolean data type, which can have only true or false values, and I'll show you some examples of that. However, it occupies 1 byte, just like a byte size. So Boolean, internally in memory, your Boolean is this the size of a byte. Just a few notes about floating point numbers or real numbers with fractional parts. And I apologize, this is a little bit of typos on the slide. So this should really say 10 raised to the 5th power right here, and this is 10 raised to the -8th power. So let me just give you an example of this to clarify. Okay, so I have a double data type, and I will call it a value right here, and I would like to initialize it. Just say equals something like this. Okay. So I use this scientific notation or exponential notation for fractional numbers. I just want you to be a little bit more comfortable with this type of notation, and I just want to show you what this is. So I'll just simply say system.out.print line, and I just will print this value. Okay, that's all I want to do. So to show you what this looks like. Okay, so we're just trying to do something very simple. Run this. Okay, and it's taking some time to build and load. So all right, so this is what it shows. Okay, so it prints this number. I'll save it for our reference like this, and notice that this value can be computed as basically 2.382 multiplied by 1E5, or 1 simply with 1, 2, 3, 4, 5 zeros. Okay, so let's compare it to like this, what we used initially, compare it to this, what I've written here, and we'll just run it again. Okay, so you see it's exactly the same type of thing, 238.200.0. Okay, so this is what this notation means really. So let's just sort of keep it like this, and 100,000 can be written as 1 with 5 zeros, or simply as this. Okay, it's like in a lot of scientific applications, what they have is like there's lots of zeros like this, and it becomes confusing. Is this like 12 zeros, 11 zeros, or 9 zeros? But if you want to specify them explicitly, it's just much easier to interpret when you do your scientific computation. So this is called scientific notation, right? And so this is how it looks like. The E, the exponent, I mean, this is called, by the way, the absolute part, and this is an exponent part, which is right here, okay, which is just the power to raise 1 in decimal base 10 numbering scheme. And so this is the type of notation which you can arguably, this is a much better choice than this. Okay, whatever, I never counted these zeros. I don't know if it's 11 or 10 or something else. Okay, but you get the idea. So basically, if I want to count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9 plus 3 also is 12, right? So this is 12. Let's just sort of like verify it like this, right? And also verify it. So again, I will preserve this result. And by the way, look how Java output, actually this print line method switched to scientific notation. It just it starts to think that this would be a wrong choice to show some kind of crazy number with lots of zeros. Instead, it can revert to the shorter form. So why show all these zeros if we can just print E12, which means, hey, just multiply it with something basically 10 raised to this power. So anyways, likewise, there's also negative exponents. So with negative exponents example right here, you take a number like we have here in our handout, and you can say e minus 8. Okay, so like I said, this notation 3.25 e minus 8 is the same as 3.25 multiplied by 1 e minus 8. Okay, and this, of course, so let's just try this just to see what this looks like. So it actually prints the scientific notation, which is fine. And the idea is that we're just going to divide this number by 1 plus 8, like this. Okay, so that's what it really means. It's basically if when the positive gives you the big number, this negative gives you the fractional number and a fraction only. So therefore you can still do it like this. So I hope it's going to be close to this. So run it. Okay, and that's exactly the same. You see this? It's exactly the same as this. So these are the formulas. So essentially, all things considered, you probably would say that that every scientist will say, okay, I prefer this. All right, so this is an exponential notation. Just to clarify what's happening on this slide. Do you need to be concerned about all of this? No. But just remember that exponential notation is nothing to be afraid of. It's just essentially converting shorter version of fractions to their real, like, you know, fully spelled out values by multiplying them by an exponent like this. Okay, so this is just something to remember about floating point number data types. Okay, now there's an interesting thing about equality of floating point numbers. Basically, I will give you an example of this, and we'll do it in our next segment.